My name is Sinclaire Manning, aka Major Merger.
And I am Sam Factor, aka MC Hammer.
And we're got some fans for MC Hammer in the house. And we're up here to present this month's Astronomy in the News. But before we get started, some of you may be wondering where AstroBit, aka Brian Mulligan, is and why he isn't up on stage with us tonight. Well, if you don't know, AstroBit is now Dr. AstroBit as of this week. And I think maybe he was partying a little too hard last night and couldn't join me. But he's in the house, so if you see him, say congratulations. He's standing up.
Yeah.
All right, let's go ahead and get started.
Okay, so we have a Mars-heavy month for you guys. 2 papers in Nature came out a couple of weeks ago, one of which talked about methane cycles in the atmosphere of Mars, and another discovering organic molecules in the rocks in Mars. So both of these studies utilized the Curiosity rover's SAM mission, no relation to me. It is called the Surface Analysis on Mars, and it has what's called a mass spectrometer. You've been seeing light spectra in the earlier 2 talks. This is actually a mass spectrum. So on the x-axis here is mass, and on the y-axis is how much there is. And you can see that there are some peaks for different organic molecules. And this has been a little tricky to find because there are compounds in the rocks on Mars which, when you put them through this instrument, actually destroy the organic compounds that you would like to find. So this study used a slightly different setting on the mass spectrometer and got some results and actually found some organic compounds. And these things, well, the word organic you might think of meaning life. Life on Earth does produce organic molecules, but there are also a lot of other ways that you can get organic compounds, mainly just involving rocks and water. So no, we did not find life on Mars yet. The other study was looking at methane in the atmosphere. You can see this nice big wave here over different seasons on Mars. This was using 5 years of data. And they think that this methane that they're finding in the atmosphere is coming from these large underground reservoirs that they don't really know where this methane or how it got in these reservoirs or how it's coming out. It's likely, again, that it's just geological chemistry that's going on. But it's very intriguing that it might be some sort of bacteria underground forming methane. We don't know. So we should keep sending things to Mars and keep looking at this stuff. So once again, no life on Mars yet, but very intriguing results.
All right, so for the first time, astronomers have directly imaged the formation and evolution of a jet from a black hole. You just learned a lot about jets coming out of black holes in our last talk. In this case, the jet is the result of a star passing too close to a supermassive black hole and subsequently being torn apart by its gravitational pull. So as the black hole tears matter off of the star, the material forms a rotating disk that glows brightly around the black hole before falling in on it. And then this infalling material is launched outward at the poles of the black hole, producing the jets that we see. So this particular black hole, estimated to be 20 million times more massive than the Sun, resides at the core of one of the pair of colliding galaxies known as ARP 229, which is the picture on the left here, and then it's an artist's rendition of what they think the black hole and the jet would look like. So at the time, it was thought to be a supernova explosion, but after continued observations, it was discovered that the material was not expanding radially outward in all directions, but just going out in one direction, which you can see in the GIF in the bottom. So that's from 2005 up through 2015 observations showing the direction of the material. So with these observations, along with New Age radio jet simulations, The only plausible explanation that Miguel Perez Torres and other astronomers found is that it must be the formation of the jet that they were observing. So over the course of a decade, the jet has released approximately 125 billion times the amount of energy the sun releases per year. And while this amount of energy should show up in X-rays or visible wavelengths, it is believed that the system is enshrouded in so much dust that those shorter wavelengths are being absorbed and then re-emitted in thermal radiation at these longer wavelengths.
Cool. More Mars stuff. So Curiosity is drilling again. In about December of 2016, the feed mechanism, which feeds the drill into the rock, not shown here, but normally this part moves up and down to push the drill into the rock. It broke. And over the past 18 months or so, engineers have been working very hard to figure out a way to drill on Mars without this feed mechanism. And they've got it working. They've figured out that it's not going to break the rover, not going to break the drill bit, and Curiosity has made its first little test drill here. So what happens is, instead of actually putting these two kind of stabilizing arms against the rock and then feeding the drill in, they're using the entire arm to push that drill bit into the rock. And this is a little bit dangerous. This is why it's taken 18 months to certify. Because there's a lot of forces, if you're not exactly centered along the hole, that could break your drill bit. But they've got it working. And also, because of this feed mechanism breaking, they've lost the ability to accurately portion out the material that they're then feeding into the science instruments on the rover. And so they figured out a way to do it that is basically like shaking a salt shaker into the input. Not quite as accurate, and they have to worry a little bit about big globs of rock getting in there, but it seems to be a good way to do things. On a slightly darker note, the Opportunity rover is in the middle of a very, very intense dust storm right now. This is actually a picture of a dust storm in 2007. This is taken during the day, and you can see over the course of a couple of days it gets very, very dark. This is what Opportunity is seeing right now, and it's basically just black static noise. It's not looking good for the rover. Curiosity is powered by basically a nuclear generator. Opportunity has solar panels, so it needs that light to keep going. And during this dust storm, it's not getting any. So it's gone into what is called a low power fault mode, where basically everything is shut down except for a timer. And every so often it will wake up just a little bit, say, are my batteries charged? If they are, it'll try talking back to Earth. If they're not, it'll shut down and wait another bit of time. So we're hoping very hard that this rover gets through it. The original mission length was supposed to be 90 days. This thing has lasted almost 15 years. So even if it does die, go NASA. So even if it does die, it's lived a very, very good life. It's produced a lot of science, way more than we could have ever have hoped for. So fingers crossed.
Okay, so if any of y'all were with us last August, you may remember during the news we presented on the story of two neutron stars merging together, resulting in the first simultaneous detection of gravitational waves and electromagnetic radiation. So for reference, a neutron star is an extremely dense, ultra-compact object that forms after a star goes supernova. And one of the biggest questions everyone was asking after the event was, what object is formed after two neutron stars collide? So Dave Pooley, who's just down in Trinity University in San Antonio, and a team of astronomers have collected new X-ray data to understand the aftermath of the merger. So X-ray radiation was generated in this collision when the merger's shockwave expanded out and slammed into the surrounding interstellar medium, and the earliest X-rays were detected 9 days after the initial merger, and continued to expand out over the first 100 days. However, if the merger had produced another neutron star in the process, there would be an additional source of X-ray emission from that neutron star itself, and by now it would be dominating over the emission from the propagating shockwave. So Pooley and collaborators don't find that excess of emission, and so that would justify the presence of a black hole rather than a neutron star. So they conclude that, yeah, GW 170817 is most likely to now be a black hole. But to confirm this, Pooley and others plan to continue observing the system for another year and gather more information on the system. So I'll let you know in a year if it's a black hole or not.
There we go. So 3 planets have been discovered actively forming around a very young star. If you've been to previous talks, you may have seen this image on the right here. This is actually looking at very cold dust that's around a very young star. And if you look closely, you can see there are a couple of rings here. Previously, we don't really know what's forming them. A lot of people like to think that they're planets carving out these rings, but there are a lot of very complicated processes that could be forming these rings. But these 2 new studies have pretty much nailed down that there are planets in this disk. And they did this by, instead of looking at the dust, they're looking at carbon monoxide gas. So very bad for your lungs, but very useful for astronomers looking at planet formation, looking at galaxies. And what you can do with this is, instead of just looking at how much light there is, you can look at what the velocity of this gas is. And here are some simulations where you're looking kind of top down onto the disk, and there are a couple of planets here. This is the density, and in this, on the right, you can see there is some velocity offsets from what you would just normally expect from the dust in the disk. So these are simulations, and these are actual data that are taken from the ALMA telescope, the Atacama Large Millimeter Array. And if you look closely in some of these frames, you can see there's a little kink here, where on the bottom you can see it's very nice and smooth, and on the top there's this kind of gap. And that is actually the signature of a planet embedded in this disk. And this is really cool because it's normally very hard to find planets that are this young, that are actively forming. And it's really cool to see that someone's actually pretty much nailed down that this is a planet and not some other very complicated physics going on.
All right, last up we have Astronomy Not in the News. So a news story that may not have made it to the big outlets, but we think is cool nonetheless, and we want to share with you guys. So a new set of cosmological simulations look to explain the dwarf galaxy population around the Milky Way and in our local group. So using high-resolution zoom-in simulations called FIRE and ELVIS, Shea, Garrison Kimmel, and collaborators worked to emulate the population of dwarf galaxies that we see nearby. So by doing these simulations, astronomers can model the formation and evolution of the Milky Way's nearest neighbors and gain better understanding of the physics required for these systems to exist. So, however, previous simulations produced a few problems, such as the missing satellites problem, which I think has been brought up before in an AOT talk. But basically, the missing satellites problem is that simulations predict that there are many more dwarf galaxies and satellites than we actually observe. But it's now believed that those simulations were maybe simply not quite advanced enough and did not include all of the physics, which is fair considering how computationally expensive these simulations are to run. So including every little detail just isn't really plausible. But the good news is Garrison Kimmel's simulation no longer produces the missing satellites problem, and they accurately produce the dwarf galaxy population of the Milky Way. So for their complete analysis, they focused on 2 pairs of local group-like hosts, which they very cutely named Romeo and Juliet on the top and Thelma and Louise on the bottom. Or sorry, I'm only showing Romeo and Juliet here, but there is a Thelma and Louise also. But you can see just how detailed these simulations can get. They can be viewed in terms of the stars on the left, the dark matter in the middle, and their gas content, and then you can view them as composites on the top and see them from all different viewing angles. But future improvements that could be made include adding the effects of black holes and cosmic rays. Like I said, it's all very complicated, and many supercomputers are required to run these simulations, but it's very exciting that they've gotten this far. And with that, that is all. Thank you very much.